Alright, so this next thing we're going to look at is I'm going to kind of talk you through 18 through 21, maybe solve a few and or help you with the setup. So for 18, it asks where you have two functions that have parallel tangents. So just my reminder that parallel tangents means that they have the same slope. So all we're looking to do here is take the derivative of both of these separately and then look and find where they equal each other. So for this first one, I'll change colors here. I have y equals x squared. So that means that y prime, or the derivative, or the slope of the tangent line, is equal to 2x. The second line, or function here, is y equals negative x squared plus 6x minus 5. So I'm going to take the derivative, y prime, and that's negative 2x plus 6. So now if we want to know where they have parallel tangents, we're going to set 2x equal to negative 2x plus 6. So I can then add 2x to both sides, so 4x is equal to 6. So x is equal to 6/4, which reduces to 3/2. Okay, the next one gives the area of a square with side length s given by a equals s squared. Find the rate of change. Rate of change usually means we're taking the derivative of the area with respect to s. So here's what I'm going to do before I do anything else. Normally we take the derivative of y with respect to x. What they're asking for this time is to take the derivative of area with respect to s instead of x with respect to y. So it's almost like this with y equals x squared, but we have a equals s squared. So the derivative of s squared is just going to be 2s. So then if we continue rating, it says when, so I'm going to put my little when bar, a is equal to 25. So the issue here is that the derivative is in terms of s, but they give us area is 25. So what we need to do here is write that s squared is equal to 25 to be able to figure out what s is. So s, if we take the square root, is equal to plus and minus 5. But because this represents side length, we're just going to use the 5. So now we're going to come and say, okay, well, the dds, or the derivative with respect to s of a was 2s. So now we have 2. We plug in what s is, which is 5. So my final answer is going to be 10 meters per second, or area, or whatever the time would be. Alright, so looking at the next one, we have find a and b so that f of x is equal to, we have a piecewise function is differentiable. So let's talk about the word differentiable. Because when it says differentiable, you have to have two things. The first thing that you have to have is continuity. And the second thing you have to have is the derivative exists. Alright, so there's two parts of that are going to allow us to solve for both of these things. So before I go through and I work the problem, I'm going to go ahead and rewrite the piecewise also as a derivative. So we've got the function, and I'm going to rewrite it with the derivative. So a is just a constant, so the derivative of a x to the third is 3a x to the second. So that's for x less than or equal to 2. The derivative of x squared plus b is 2x. And that's for x greater than 2. So the first thing that I'm going to do here is I'm going to look at the limits of the derivatives. So we're going to write that the limit as x approaches 2, and I'm using 2 because 2 is that split point where we have potential issues, from the right of f prime of x must equal the limit as x approaches 2 from the left of f prime of x. So now we're going to plug in 2 for x into the derivatives. So from the right is going to be that bottom function, so we end up with 2 times 2, which is 4. In the top function, we're going to plug in 2. So we get 3 times 4, which is 12, and then we still have that a. So if 4 is equal to 12a, then a is equal to 4 divided by 12, which is going to reduce to 1/3. So using that the derivative must exist and the limit from the left and right have to equal each other, we're able to solve for a, but we also have to solve for b. So that's where we can use this definition of continuity. So we're now going to come say, for this to be continuous, the limit of the function from the left must equal the limit from the right. So I'm going to say that the limit as x approaches 2 of f of x from the right must equal the limit as x approaches 2 from the left of f of x. So now we're going back to the original function. So if we plug in 2 to the right, that's going to be the bottom function. We get 2 squared plus b, which is 4 plus b. If we plug in 2 from the left, that's plugging in 2 to the top function, which is going to be 2 to the third, which is 8 times a, so 8a. And if this is all you were looking at, you'd have a problem, right? Because we still have a and b in the answer, but we now can plug in 1/3. So 4 plus b is equal to 8 times 1/3, or 8/3. So now I'm going to come and say, okay, so to find b, we're going to take 8/3, subtract 4, which is 8/3 minus 12/3. So my final answer, b, is equal to negative 4/3. So I now know b, I already found a, and we're done with that one. So using the definition of differentiability with the aspect of if it's differentiable, it must also be continuous is kind of the trick to help us find both pieces there. So the last one, 21, is a little bit of a complicated process, so I'm going to actually take out a separate sheet of paper to help us. So I'm not going to solve this one all the way through, but I am going to help you with the setup to figure out what it's asking. So it's asking us to find any tangent lines. Okay, tangent lines meaning the derivative is the slope and the function gives us points. So kind of keep that in mind. We might have to plug back to the function and the derivative once we find x. So it's tangent to the curve that goes through the point 1, -9. So maybe the point is 1, -9. So that might have been a little extra. So find the tangent lines to the curve. So I'm going to come sketch this for you. So y equals x to the third minus 9x. So I'm going to write this a little bit bigger than maybe I would normally, just so you can see. So the first thing I'm going to do is I'm going to sketch this. Now I probably could do it, at least get close without this, but I'm going to come put this in a calculator. So I did this earlier. If we look at x to the third minus 9x, we have zeros at -3, 0, 3, and we get this polynomial function. So it doesn't have to be perfect, but I'm just going to kind of sketch, okay, it's going to go through -3, come up 0, and then somewhere dip back down. So here's what the graph looks like. We have another point, 1, -9. So again, it may not be exact, but we have this point. So again, I'm not worried about the perfection here, but what it wants is a tangent line that goes through that point. So the thing that I guess people may or may not realize is that that point is not actually on the curve. That point is out in space. The point that's on the curve is what we don't know. Alright, so I'm going to call this negative 1, 9. Whether or not this is exactly what it looks like, it's just kind of more for, 1, negative 9. 1, negative 9. 1, negative 9. So what it wants is it wants us to write the equation of this tangent line here. The part that's kind of tricky is that we might have to use two different things to be able to find the slope of this tangent line. Now if we knew that this point right here, then we could just take the derivative and plug in x, but we don't know that. So the first thing I'm going to do is I'm going to write y prime. Okay, so y prime is equal to 3x squared minus 9, and again represents the slope of the tangent line. However, in order to find that numerically to write the equation of a line, we need to know what x is. And again, we don't know what x is. So I'm going to call this a, because I don't know what it is. And if that's a, then this point here is the point a. And since it's on the curve, we can come plug into the original and replace x with a. So a to the third minus 9a would be the y value. So here's what's kind of cool, is that the derivative represents the slope of the tangent line. But if we have 2 points on the tangent line, then we can use the secant slope of these 2 points, which also represent the slope of the tangent line. So we're going to use y prime, and we're going to also use slope formula. So I'm going to say that y prime, which is the derivative, the slope of the tangent line, is going to also equal the secant slope given those 2 points. So in order to set up this change in y over change in x, I'll say this, that we need 0.1. So 0.1 is going to be 1, negative 9. And we need 0.2, which is that a to the third minus 9a. So now we can write a slope formula. So if we want to know change in x, or change in y over change in x, it's going to be a to the third minus 9a minus negative 9. That should be a 9. My a's and 9's look a lot alike, so I apologize for that. A minus negative 9 over our change in x, which is a minus 1. So if we clean that up a little bit, we end up with the derivative, which is 3x squared minus 9, equal to the secant slope of 2 points on the tangent line. So this is a to the third minus 9a. The double negative makes it a plus 9 over a minus 1. So here is the setup. So what we want to know is where those two things equal. So the rest of this is just going to be a matter of solving and figuring out how to find that a value. So if I write this over 1, I can cross multiply. And let me backtrack a little bit. We're going to end up plugging in a for x into both of these. So now we're solving for a. So this becomes 3a squared minus 9 times a minus 1 equal to a to the third minus 9a plus 9. We might have to FOIL that left piece. So we end up with 3a to the third minus 3a squared minus 9a plus 9 is equal to a to the third minus 9a plus 9. And if I add 9a and subtract 9, add 9a and subtract 9, the a's and the 9's are going to cancel. So to clean this up, I'm left with 3a squared, or 3a to the third, excuse me, minus 3a squared equal to a to the third. And since we have a to the thirds and a squareds, we're going to have to solve this by factoring. So I'm going to subtract over. So I have 2a to the third minus 3a squared is equal to 0. If I factor out a squared, I'm left with 2a minus 3 is equal to 0. So if a squared equals 0, my first answer is a equals 0. And if 2a minus 3 is equal to 0, then my second answer is 3 halves. Alright, so a gives me the x value. Reminder, it asks us to write the equation of tangent line. To write the equation of a tangent line, we need slope and we need points. So I'm going to first say when a equals 0, and I'm going to go through that one. So when a equals 0, to get the point, we're going to plug 0 into the function. So if we plug in 0 into the function, we get the point 0, 0. And we need the slope of the tangent line. To get the slope of the tangent line, we plug into the derivative. So the derivative is going to be 3, we said, times 0 squared minus 9, which is negative 9. So when we write the equation of a line, it's going to be y minus 0 is equal to negative 9 times x minus 0, which could reduce to y equals negative 9x. And you'll do the same thing. You'll let a equal 3 halves. You'll plug into the original to get the point, and you'll plug in the derivative to get the slope.